today's PSUG is on low temperature geothermal systems, which is particularly useful for us. Boise sits on one of the largest and oldest low temperature geothermal systems in North America. Okay. But today, some housekeeping items. This lecture series is sponsored by the Idaho Power Company. They pay for my time, the speaker's time, and the food. So please help yourself to some tacos. Here at the IDL, we're dedicated to the education outreach of high performance, energy efficient building design. Some programs that the Idaho Power Company also sponsors is the Energy Resource Library. This is a free resource for Idaho Power customers. You have to be an Idaho Power customer to use the library. We have over 900 building diagnostic tools, so it deals with electricity or energy in some fashion. Chances are we have a tool to measure and verify its performance. Next month, we're having another PSUG. It's going to be a joint session with the Idaho ASHRAE chapter. We're having Christian Calvary, very, very smart man. He's leading ASHRAE and AI right now. He's one of the top people on the panel. I went to a lecture of his 2 weeks ago. It was very awesome. But he's going to be talking about BIM to BIM, building information modeling to building energy modeling. And I'm going to go out on here and say he's probably going to tell you about how to keep AI for that problem. Next, we have the Lunch and Learn lecture series. This is a hybrid format. We can come to you in your office, and if you have people remote or not in the office that day, they can view it online. We also host 4 of them here at the Water Center for anyone to come to. If you would like to have a lunch and learn for your firm, please contact me at that email. Next, we have technical design assistance. So the IDL can provide varying levels of energy efficiency and technical assistance. Depends on the scope of work. It's broken up into 3 phases. So less than $2,000. That could be, hey, there was a software update to Revit for insight energy analysis or daylighting, and something's not working anymore. You can call me up or send me an email. I can look into it. If you have a question about energy codes, how that can be applied, or what you're doing on your project is applicable, that's something else. Phase 2 is $2,000 to $4,000. It's a little more in depth. Has an actual formal scope of work, and then anything over $4,000 is a phase 3, and that's a cost share agreement with Idaho Power, with Idaho Power covering 75% of it and the client covering 25%. And lastly, Sheree, did you want to speak? Sorry, or Andy.
Put my last.
Put you both on the spot.
Well, you're here.
Yeah, I just took a bite too. Sorry.
Just to remind you about our energy efficiency programs. We have energy efficiency programs for residential, commercial, industrial. We have both prescriptive programs as well as a custom program as well for stuff outside the box. So feel free to reach out to Andy or I, and we can help you with that if you've got a project.
Okay. With that, I want to introduce our today's speaker, Carter. You can go ahead and share your screen. Carter is a geothermal scientist who has specialized experience in geothermal systems. Received a Bachelor of Science from Brigham Young University, Idaho, with a minor in GIS. He also completed a MS in Sustainable Energy Science with a special focus in geothermal systems, where he specialized in numerical and chemical modeling of high temperature geothermal reservoirs. He has technical expertise in a variety of geothermal issues, including well design, power plant design, life cycle analysis, numerical reservoir simulation, reactive transport modeling of reinjection fluids, and energy markets and economics. He currently works as the chief scientist for Geo LLC. So, thank you, Carter, for joining us today.
Thanks for having me. It's a big crowd. This is a lot of people on here. I'm excited about it.
Okay. Carter, before you get started, we're seeing the presenter mode
Okay.
on our side. You click the 3 dot in the circle.
Try this again. Oh, strange. You're still seeing my screen though, right? You just see
Yeah, we're seeing
the
all
whole
of,
PowerPoint.
yeah.
Well, let me try one more thing, and if it doesn't work, then I'll just share like this. I'm just gonna try to share just the PowerPoint from here.
Okay.
All right, well, we may be stuck here unless you have some advice for me.
Try turning off your video. That might help with the connection.
Okay.
ChatGPT says that if you're in slideshow mode in PowerPoint, that it might not stream through Teams.
Okay, well, we're doing Zoom.
You can see my screen though, right? I mean, you just see
Yeah,
all of
we
the options for
yeah, we
PowerPoint.
could do it this
Well,
way.
why don't we just get started? At least we can still see the information. You okay with that?
Yeah, that's fine with me.
Okay, my apologies for that. I don't know why it's not working. Okay, well, we'll get started. I'm Carter Johnson. Thanks for the introduction. A little more about me. I'm from Las Vegas. I currently live in Salt Lake City. Like you said, my background's in geology, and I have some specialized education in geothermal systems. I studied in Iceland, where I learned lots about high temperature systems, how to use low temperature water after it's already been run through a power plant. I did some numerical modeling um, and some chemical modeling while I was there, and some pictures of me while I was studying there. Got to see the volcano erupt. It was a great time, learned a lot. A little bit about this presentation. First, I'm going to cover worldwide geothermal uses, just to get a good grasp on how this resource is being used everywhere, all its different kinds of uses. We'll talk about types of geothermal systems. So we'll touch just briefly on high temperature stuff, including some direct use and power production, baseload power, a little bit about low temperature exchange, but mostly about ambient temperature, which I think is particularly interesting because it's available anywhere. Even in Boise, I mean, you guys have a good low temperature aquifer. It's good for direct use. Um, but even though the resource it exists, it can be hard to get to. I think in a lot of places in Boise, you have to drill at least 1,200 feet deep to get to it. And there's some issues with drilling permits right now in that area. So once again, to just be able to use this ambient temperature water close to the surface um, has a ton of advantages. We'll end on talking about the potential of thermal energy networks. Okay, so worldwide geothermal use. So just a few definitions to get us started. So a system refers to all the parts of the hydrological system involved. So there's a recharge zone, there's all parts of the subsurface, and also the outflow of the system. When we talk about a reservoir, it indicates just the hot and permeable part. When we say direct use, we're talking about a direct application of hot geothermal fluids. And I mean, hot is relative. It's anything that can be used directly for space heating, greenhouse heating, and a bunch of other uses. Some of the most common are snow melting, bathing, and heat pumps. And then last, when we say ambient temperature, this indicates there's no actual geothermal reservoir. So the system is designed to use the steady temperature of groundwater for heating and cooling systems mostly. So worldwide, this is a few years old, but this is to give you a sense of how we're using this resource. As you can see, the dark green countries are direct use in electricity production. And these are some of the big players like United States, Japan, Iceland, Indonesia, a couple of countries in Eastern Africa along that rift zone have some really good hot water. And New Zealand is also very notable. As far as direct use goes, though, I mean, the majority, almost 70%, is being used for heat pumps. Some of these other ones include bathing and swimming, very popular, very easy to use. Space heating, aquaculture, greenhouse heating, and then some other industrial uses and agricultural uses. So it's utilized in more than 90 countries worldwide. As far as high temperature resources go, really just found in volcanic regions and then some hot spots. As of right now, with current technologies, there are only about 180 high temperature reservoirs worldwide that we're using. That number is going up and up as we get better technology that can harness lower temperatures for power plants. And so now you may have a new fluid that vaporizes under lower temperatures, and so now you can run a really small turbine. But that number, it's not going to change a whole lot. I think it's gone up from 160, 170 a few years ago, and we're getting a little better at it. But we're pretty limited, about 180 reservoirs we can use for electricity production right now. Low temperature resources, however, are distributed throughout the world. Boise is a good example where I think that your hot water is from radiogenic heating. You have an old granite that's breaking down, and as that breaks down, it releases some heat. And these are much more common. You see these low temperature resources all over the world. And even more readily available are the ambient temperature resources. Most places have groundwater. We need to do a better job at using it responsibly, but it's there and it's available for these applications. One more note before we move on to more of this low temperature stuff. In the last few years, there have been some huge advancements in what we call enhanced geothermal systems that could change the landscape of how we look at energy and geothermal energy. Essentially, what we're doing here is we're using oil and gas technologies to create our own reservoir. Geothermal reservoirs usually require a few things. First, permeability. You have to have cracks and fractures and porosity in the rock for water to move through it. You have to have heat, and then you actually have to have the water. Well, a lot of places have the heat, but don't have the fractures or the water. So new technologies are coming out that essentially fracture the rock, usually using high pressure and proppant that props open these fractures. And then what you're doing here, as you see in this figure, is you pump cold water down into this artificial reservoir, and you're using the natural geothermal gradient of the earth, and then you have production wells that are producing that water that's been heated by the artificial reservoir that you've created. And we'll see how this changes in the next couple of years, and it's an exciting time. There's lots of money going into it. just worth it to note. That's a new technology that you can keep your eye on. Okay, ambient temperature geothermal. So most of this relies on heat pumps, and these work on principles that utilize that ambient temperature groundwater. Ambient meaning you're just following the natural gradient of the earth. It's usually no more than 850 feet. This is changing also. There's lots of drilling companies now that are drilling 1,000 feet or more with no extra costs. Something else that's great about this type of geothermal is there's no, it's really simple compared to the high temperature systems in a lot of ways, right? You're not worried about magmatic intrusion, about how decay rates are going to affect it. You're not so worried about taking care of a geothermal reservoir and planning injection and making sure that you have high pressure. It's a little more simple than that. Another advantage, and this is mostly in really warm, arid regions, the stable temperature of the earth. You can use cool water that's cooler than the outside temperature, so you can extract it for just space cooling. So a little bit about heat pumps. Like I said, I'm not an engineer, I'm more of a scientist. A lot of this is kind of magic to me, how we can run these refrigeration cycles. Um, so we'll get through this and get back to the subsurface stuff. But I mean, this is essentially how it works. It works like a refrigerator, and it can be air sourced or water sourced. And what you're doing here is you're essentially sourcing air or water, or you're sourcing from the ground. You have a refrigerant loop inside of the house that leads to a heat exchanger and then to a home loop where you're heating your home with radiant heating and hot water pipes or with air ducts. Something that's important to remember about air source versus these geothermal ground sourced heat pumps is their COPs change a lot when the outside temperature changes, right? The constant speed COPs are published as these as good COPs, but there's no publications on how they respond to ambient temperature, outdoor temperature as the air changes. So you're getting a lot more constant COP with your ground source heat pumps. We're going to change gears a little bit and talk about what geothermal technologies exist to harness that heat from the ground, this ambient temperature heat. And there are three main ones we'll talk about. There's lots of variations on these, but we'll talk about closed loop, we'll talk about open loop, and we'll talk about submerged heat exchangers, which is kind of a combination of the two in some ways. This first one, closed loop, essentially what you have is a totally separate system where you're running fluid through usually U-tubes installed into the ground that are either harnessing heat from the ground to heat your home, or what you're doing is you're dumping heat into the ground. And here's some more layouts of what this looks like. Like I said, that U-tube version is probably the most common, where you just drill boreholes and you insert U-tubes into the ground. There's a bunch of variations on this, whether they're coils, all sorts of things depending on how deep you want to go and the type of ground you're looking at. Something else that's new on this figure on the right is angled drilling. So what you're doing here is you're decreasing the surface area that you need to be able to drill more wells, where I think there's like 10 in that picture, and usually you have to have 15 to 25 foot separation between the wells. Well, with new drilling techniques, you can drill them at an angle, and you really only need, like right here, a 4x4 foot space to drill that same amount of wells. And this is what an installation can look like for vertical closed loops, where they've basically just backed up that truck into, it looks like someone's backyard. We're getting better and better at this, and drilling rigs are getting smaller and smaller. But then afterwards, I'll skip to this one. Afterwards, it really looks great. This is what it looks like after most everything is installed underground, and you can cover it all back up, and very, very little space is actually taken up by the installed systems. Here's a picture on the left of what these some of these new drilling rigs look like, where they're really only some of the smallest ones are 2 feet wide by 4 feet long, and then you need about 6 to 8 feet vertical to be able to get the casing in and the drilling and to do the actual drilling, which unlocks new areas that we haven't been able to drill before, whether that's like getting a drilling rig into someone's backyard, or something new in really dense urban areas is getting drilling rigs into parking garages, where you can get in there and you install a whole geothermal system in the parking garage, and then you cover it back up and it can still be used for parking afterwards. So before I move on, this closed loop is really advantageous because it does not rely on aquifers. You're not pulling water out of the ground. You're not putting water into the ground. Really, what we're dealing with is just heat transfer from the fluid into the subsurface. It makes it really simple, and it makes it easy to apply almost anywhere in the world. Okay, next we'll talk about these aquifer-based exchange systems. And the two we'll talk about are dynamic closed loop, which is the one I mentioned is kind of a mix of the two, and then your traditional open exchange wells. So the dynamic closed loop, lots of names for this, but the most common name you're going to see is submerged heat exchangers. And it's essentially just that. Instead of running a fluid up into the heat exchanger into your home, they've installed the heat exchanger directly into the borehole. And then what we do here is we have an injection perforation in the well, as well as a production perforation in the well. And so instead of having two wells that are separated geographically or horizontally, we have one well, and your injection and production segments are separated vertically. And so you're running water through the heat exchanger underground in this well that's connected to a closed loop system that can pull heat out of that heat exchanger and then into the home. And the reason for this is because what we can do is we can have less wells, and we can save some surface area that we need with your traditional closed loop systems. I'm going to see if I can play this little video for you guys here that shows what this probe looks like.
The energy prices are becoming prohibitive. The DCL geothermal system can help solve this problem.
Hey, Carter, we're not seeing the video on our screen.
Is it not coming through?
We hear the audio, but the visual is not. They're still on the PowerPoint.
Okay, well, let's not mess with that then. Let's just get back to the PowerPoint. Worth a shot. Then our last technology here that I'll get into is your more simple open loop aquifer exchange. And this is where you have usually two wells, or at least one doublet system. One of them is a production well, one of them is an injection well. You're producing water from one well, running it through a heat exchanger, and then you're injecting that water back into the ground. This one and the previous concept I talked about, the DCL or submerged heat exchanger concept, both rely heavily on the ability of the ground to yield water. And that can get complicated depending on the rock type. You might be dealing with secondary permeability or large fractures that run through the rock. You also need to start to consider which direction the groundwater is flowing. For instance, if you have your injection well upstream from your production well, then you may run into short circuiting problems where you're just reusing the water so quickly that it can't stabilize its temperature before you use it again. So I'm going to share with you guys a New York City case study that we just finished that maybe will help you guys understand some of the questions we ask when we're trying to decide on a technology like this. So we just finished a project in New York. It's 3 buildings. It's about 450,000 square feet of conditioned space. And this is it's Village East Towers, and it's right downtown New York City, on Manhattan Island. So lots of buildings everywhere, not a ton of drilling space. And they're trying to decarbonize. There's local law 97 that's coming up. They're going to start getting taxed for all of their carbon emissions. So they're really doing anything they can to cut down on those. And so they wanted us to investigate a geothermal system. You start by analyzing utility bills. We use a modeling system that essentially gives us the peaks and all of the heating and cooling loads that we need to meet with a geothermal system, which comes out to about, I think the peak is around 1,200 tons. And to give you some reference, I think 3 to 4 tons of heating and cooling is a standard family home. What we do first is we start with a geologic investigation. And unfortunately, in this case, there weren't a ton of wells right near the site. So what we did was we actually created a geologic model for the entire peninsula, and then interpolated some of the data points between the data points to get elevation and geologic characteristics on site. So from this large model, we then cut it down to just a slice of the peninsula so we could see what's going on the actual site. What we're looking at is about 118 feet of glacial till, which is the really permeable rock that we're interested in for the aquifer, followed by at least 800 feet of a gneissic bedrock. We did some investigation into the direction of the groundwater flow. It generally follows topography, so your flow is going to go from north to south with a little bit of a slant east to west. And you can see some of the drilling spaces that we've identified here as well. We did a site visit and we said, okay, we can back up a drilling rig into these places and maybe around here, around outside the buildings. We also need to consider some aquifer information before we decide the technology. Groundwater exists 10 feet below the surface at the site. Aquifer yields in the glacial till range from 20 to around 200 gallons per minute. Usually what we're looking for is something a little more decidedly good or bad. When you have these large ranges here, you start to get into some risk. And that was all dependent on local differences in geology. Some places had a lot of clay that made it hard for water to get through. Some places were much more your traditional glacial till, and it yielded a lot more water. Aquifer yields in the bedrock also have a range 0 to 100 gallons per minute. Most of the time we're looking at 0 to 10 gallons per minute, but some fractures that run through that rock can produce up to 100. So once again, not a very reliable aquifer in either of those formations there. So we first started by looking into closed loop geothermal, which once again is that totally separate system. You have U-tubes installed in boreholes that harness heat from the earth. Doesn't rely on aquifer characteristics. We use a program called GleePro. And the inputs include heating and cooling loads. They include your borehole depth and diameter, heat transfer characteristics of the ground, and then also location that helps you determine the climate and how the temperature changes throughout the year. One other thing that we considered is there's a parking garage on site that we can get a drilling rig into. And so we had a little bit more extra space to work with here using that new technology. At first, we considered the standard 500-foot wells at 15-foot separation. This would require about 400 boreholes. and about 170,000 square feet, which was a lot. It was more than what we had available. We contacted some subcontractors who specialize in angled and deep drilling, who can drill 1,000 feet deep for the same cost and also decrease some more of that surface area using angled wells. And we were able to meet the load with 210 boreholes and only about 100,000 square feet, which significantly reduced what we needed to do here. And once again, this technology had no reliance on aquifer yields. The next technology we considered was that submerged closed loop heat exchanger. These require 50-foot separation. In this case, we estimated it would require about 21 boreholes and 52,000 square feet, a significant decrease from the closed loop. I mean, almost 200 less boreholes, about half as much space. An issue we ran into these in this area is that you need at least 100-foot separation between the upper and the lower perforated sections in order for it to run properly. And it does rely on aquifer yields. Most of the time you need at least 150 gallons per minute, which is possible in some places in this aquifer, but like I said before, it's not super reliable. And then the last one we looked at was the open loop, where you have wells that are separated, and you're producing and injecting water back into the ground. Something we do a lot of times for these is we do a numerical model. So you run simulated wells on that geologic model that I showed before, and you can also simulate the flow of groundwater, and you run the wells for 25 years, producing and injecting, and then you see how they do over time. You see where the thermal plume is going to go, if you get thermal short circuiting. In this case, we ran a model, and we were only able to get 4 production wells and 4 injection wells on site. These usually require about 1,000-foot separation. To meet the loads, however, we needed about 14 production and 14 injection wells. So required far too much space for this site. We figured we could implement this if the aquifer could yield much more gallons per minute. It ended up being something like 800 plus gallons per minute that we needed to be able to fit it on this site. So in this case, we decided to go with the closed loop system. It made a lot of sense. And that's one reason why these are so popular. They don't rely on these aquifers. There are some other cases where, for instance, the submerged closed loop heat exchanger would have used a lot less wells. It probably would have been a little cheaper. It uses a lot less space. But in areas like this where it wasn't reliable, we just couldn't implement something like that. So this is what the system ended up looking like. You can see the closed loop field in the middle that provides most of the heating and cooling. Another thing going on here in each of the 3 buildings is what we call a piranha unit. And I'll talk about these a little bit more later, but these are units that use wastewater. They gather heat from the wastewater and recirculate that heat to provide hot domestic water. Okay, this is the topic we'll end on. I'll talk about thermal energy networks, how these technologies play into them, and sort of what we're looking forward to in the future for these thermal energy networks. So a quick history, this used to just be district heating because that's all these networks did. But I mean, really early on, 1300s, France supplied 40 homes with hot spring water. And that was sort of the basis of this. You have hot spring water, gets cold in the winter, we're going to heat our homes with it. In the late 1800s is what we call the first generation of thermal energy networks. And that's when we started to use steam to supply networks to buildings. Eventually, these were replaced by systems that utilize pressured and hot water. We start to see a move away from these pressurized systems and these really hot systems. We start to move towards lower supply temperatures and prefabricated pipe materials. Some of the reason behind that was because if you had a pipe failure or a valve failure or something, that pressurized hot water caused a lot of injuries. And so ever since then, we've seen more and more lower supply temperatures and better pipe materials. Picture of Birdsall Hawley looking at the first ever district energy steam mains. And then what we're looking at now, 4th and 5th generation district heating systems. These focus on smart integrations within existing grids and using lots of different heat sources across the same network. So in this example, we have solar, wind, we have a bunch of different uses, different building types, all connected together with modern control systems. This is a good diagram that shows just how integrated different pieces of these thermal energy networks can be. You're connecting multiple buildings into a shared network. It can include geothermal boreholes, surface water, wastewater. Number two, there's wastewater energy transfer going on that extracts heat from sewers. Heat is conducted in and out of mechanical systems of buildings. Lots going on here. I want to talk about number six, recreational facilities such as ice rinks and water parks may be connected, depending on the use, and especially really sort of niche buildings and uses here, like an ice rink or like a data center, or um, we like to use the example sometimes like different exhibits in a zoo might need different temperatures. When you can connect lots of different uses together like this, what you get is really high efficiency in these large thermal energy networks. And this is a simplified version of that where you see, I think your bottom axis is number of connected buildings, and then the left side is your load diversity multiplier. And so the more buildings you can get connected to a thermal energy network, the less energy you have to provide is essentially the gist of this. Surface water exchange is another big part of these. This is the one that I'm the most familiar with. It's called the Slim Jim Lake Plate. And these are used in lakes. They're also used in rivers. Um, and this is a great sink for heat that can be added to all sorts of thermal energy networks. Another one is wastewater. These are the units that I use the most for my projects. They're reliable, they're small, they can fit in most mechanical systems. They hook right up to your wastewater, and I think most wastewater comes out at around 70 degrees Fahrenheit, which is plenty to be used for domestic hot water. Most projects where we use these, we can meet all, if not most, of the domestic hot water demands with Piranha units. Another system that's being implemented in many of these thermal energy networks is thermal energy storage. And there's lots of different ways to do this. The diagram we're looking at here is aquifer thermal energy storage. And what that means is you're dumping either hot or cold water into the aquifer and then extracting it seasonally to heat or cool your home. Like some of these other technologies, this is heavily reliant on subsurface characteristics. You need a confined aquifer. So you can see here there's a confining unit, this brown unit, and then the yellow aquifer, and then another confining unit below it. This is really important for these systems. You also need very little groundwater flow. Otherwise, you dump your thermal energy storage into the ground and then it gets swept away after just a couple of months. Alternatives exist for these, like putting storage containers underground, and then you're not so worried about the subsurface characteristics. Another popular one, especially in Europe, and if it's a new building that's going up, is energy piles. So what you're doing is you're essentially installing a closed loop system. But if you have to drill for these piles anyway, or for these building foundations, then it costs very little to just throw in a geothermal system into these piles. I did an exchange program in Italy where I studied these, and amazing the amount of load you can meet just by putting a geothermal system in while you install the building. And these are, I mean, they can be used in energy piles, lots of different foundations of buildings. I've seen them used in subway tunnels even, where as they install a subway tunnel, they also install the geothermal system. So once again, lots of uses for these. Another thing that's important is as you install these geothermal systems, most, if not all, of your equipment is being installed underground. So not only does it look better, you don't have all of these outdoor AC units and piping um, and outdoor equipment, but also it's safer. You don't have to replace it as much. You have a storm or a hurricane or something come through. You have reliable heating and cooling. You have reliable systems in place. Okay, I'm going to end on just a couple of examples that we've been working on of these thermal energy networks so you can see um, just how some of these things come together. Um, so in this case, there's a good aquifer. So we were able to use an open loop system as well as a closed loop system in another geologic formation that didn't yield quite as much. Um, there's surface water nearby, and there was also a water treatment facility nearby. Nearby, we were able to link in. Um, Also fortunate that in this case there were lots of commercial and residential buildings, which is good to get different use types together. Stockholm, Sweden has a really interesting thermal energy network that they've worked on. Energy from the sorted city waste, so lots of heat from that, heat recovery from sewage water, district cooling returns, and data centers, which are getting bigger and bigger, provides an interesting sink to add to thermal energy networks, as well as renewable energy from biofuels, and they have lots of investment into essentially ocean power, where they um, harness tidal power as it comes in and out. Last, I'll talk about data centers. Like I said, these are getting bigger and bigger. They're only going to grow in the future, and we need to be able to meet them with clean technologies. And geothermal will play a large role in that, whether it's closed loop or open loop, being able um, to provide energy for them and being able to use them as a heat sink in these thermal energy networks in the future. So just a little bit about the trends we're seeing with thermal energy networks and geothermal in the future. New drilling technologies are coming out every year. In the last 6 months, drillers have um, have gotten back to us and can now drill down to 1,200 feet deep in most cases. Where just 2 years ago, they really all of our drillers wouldn't go past 600 or 700 feet. Just to give you an idea of how quickly things are changing. The angled drilling as well will unlock new locations for bore fields. Places like New York, where they're trying to decarbonize but don't have very much surface space available. It'll be big there. Energy agnosticism is growing, where we're learning to utilize all forms of heat sinks and sources, whether that's wastewater, data centers, or combined heat and power. We're also learning to design thermal energy networks in loops to make the growth of these networks cheaper and more practical, where you might not have funding or maybe the construction is too complicated. So instead of designing it for the entire city, you design it for one central loop, and then you can do construction or you can grow it as you want by connecting more loops onto this one central loop here. And that's becoming more and more common in these thermal energy networks. So just a few conclusions. We're seeing a growth in green renewable energy sources. This isn't just, I talk about this a lot, but this isn't just something that I think morally and sustainably makes sense. But I mean, you want to talk about a a business idea too. I mean, you to have a sustainable source, something that's not going to run out eventually, makes sense, I think, morally, and it makes sense economically. Geothermal has made a huge contribution to world energy needs, especially direct use, which is growing. It's grown at least 10% every year since 2005. And of that, geothermal heat pumps are the fastest growing use. Unfortunately, I don't think geothermal is very well known, and especially not all of the nuances of it. I think that people think geothermal and immediately think power plants, or they think about um, the geysers or Iceland, and there's so many more uses of it, especially these ambient temperature uses we just talked about. These energy networks are limitless and can be applied nearly anywhere and can integrate dozens of sources and sinks. Okay, and that's all for you guys. Thanks a ton for having me. Are we going to do questions, Dylan?
Yeah, thank you very much, Carter. So I'll go ahead and unmute yourself, ask your question.
Hey, Carter.
Hi.
Yeah, hi, this is Todd Greenwell with Idaho Power. Thanks for this great information. It's encompassing. I just had a question if you had an opinion on something. You know, the fact we have geothermal water, not necessarily ambient water you're talking about also, but the fact that, you know, we're sitting with 150, 160 degree geothermal water that's been used, like you're talking, for district heating, for direct use, district heating, power production. We dabble in
You're
some of
talking
that
about in
stuff.
Boise?
Yeah, I'm sorry. Yeah, Boise. Do you see, as this, I say Boise as an example, or anywhere else in the United States where, and I know you need to use this stuff responsibly, this resource, but this becoming potentially the waste, I don't want to call it waste heat, but the heat source to couple with high temperature heat pumps to get heat pumps into the industrial sector that need the 200 to 600 degree Fahrenheit to do their thing. I mean, you know, or like you mentioned, Sweden, you know, Europe, Japan, with the companies like Spilling, Epcon, GEA, Heaton that are into that heavily. I don't see it in the United States other than Johnson Controls, maybe a Carrier dabbling in it. But this is crazy. It drives me nuts because it's nothing. I know we have different, you know, low temperature or low price natural gas, but what are your thoughts on the potential of ever getting this heat source into heat pumps to bump it up on the temperatures for processes?
No, that's the question. And you know, I don't know. I think about that a lot, where we have lots of these technologies and really great examples that are being implemented in Europe, in places like Sweden or in the Netherlands. They do a really great job at this. Um, I don't know if some of this is that we have less. Um, we think we have less moral responsibility in America, or like if it's a cultural thing, or if it's just that it's been more developed over there and we're just taking a little bit longer to get it implemented here. Um, I don't know, man. I think that that's kind of the million-dollar question is how do we get it more implemented here? If you ask my boss Jay that, he would say the issue here is education, and he's huge about education. He publishes books, he writes articles, he's on LinkedIn every day. I mean, I do think that's part of the answer is people just don't know about it. We just don't know how easy it is. We think it relies on volcanic systems, and really it's ready to go. It's ready for all of us. So.
I guess as follow-up, do you know if any of these manufacturers, I mean, it's like 2025 out in Europe, are any of them running around the United States trying to sell their wares to these industrial sectors? Are you aware? Are they trying to penetrate the U.S. or are they just leaving us alone? Because I don't know if it doesn't seem to be ever get developed in the country, but you know, if they're trying, I just see an increase. I'm not directly involved in commercial, but I do see an increased appetite from CEOs to decarbonize in certain cases, but they're looking at something other than vapor compression. I mean, electric resistance, obviously, but
Yeah.
it's scary. I mean, to me anyway.
No, I agree. And we do see more of that. This last year and a half or so, I've had more meetings with European companies looking to implement their technologies in the US than ever before. And more marketing white papers I've written in this last year for European companies trying to get into the North American districts. So yeah, it's definitely out there. It's definitely growing. I think once again, I think there have been policies that are hard to deal with. There's funding, all sorts of issues, but we do see an increase in it, and it is growing, and they're making their way over here.
Thanks, Carter.
Yeah, good questions.
Hey, Carter, another question from online. Is there any environmental concerns about using the aquifers?
Environmental concerns?
Yeah. Melinda, if you want to clarify, you can unmute yourself.
I don't know if you can hear me. Can you hear?
Yeah, I hear you fine.
Oh, good. Well, if you're tampering with aquifers, my concern was any do you foresee any environmental impacts that it may have? You know, either something goes amok, you're talking about um perfect situations, but
Mhm.
we know that things happen, and hurting the aquifers may cause more damage in the end than using this as a source. That's all I'm trying to look at.
No, I see what you mean. And you know what? Usually when we design these systems, they're so safe and they're so foolproof in a lot of ways. That usually we're more concerned with, how do I put this? When we design a system like this, usually the issue is that the water has already been contaminated by something else, rather than we're worried about the geothermal system contaminating it in any way. I mean, the only thing that I could think could go wrong is somehow you have a leak in your glycol system and now you've put glycol into the earth. But I mean, even something like that, your closed loop system, all of those fluids are designed to break down naturally. I can see where data centers have complications where usually what they're doing is they're using cooling towers that use the water, which is a big concern. We're already running out of our clean, fresh water. But I mean, very few cases where a geothermal system has actually damaged the aquifer in any sort of environmental way. The bigger concern is what are we using the water for, and is it getting back into the aquifer? Um, and then temperatures. Are we heating up the aquifer or are we cooling it down? And how is that going to affect our use in the future?
Yes, I agree. Thank you.
Yeah, thanks.
I got a question.
Okay, go ahead.
Yeah.
I've done some some simulations with GleePro also, and you see some temperature gradient over time. They'll do a 10-year simulation. I'm curious if you've seen that in measurement or measured data as well. I've heard anecdotally that things really don't drift that much. Curious what you've seen.
So we have, and I mean, I'm new enough to the industry, but I haven't designed enough systems that have been in place for 10 years to see how they respond. Um, You're right, and you're right. The simulations do show usually, especially if it's not a balanced load, they'll either heat up the ground or they'll cool down the ground. But a lot of these really early systems, and some of my coworkers who've been in the industry longer would tell you they've designed systems that weren't balanced properly, and they either completely cooled the ground, they couldn't get any more heat out of it, or if it was lopsided the other direction, they heated up the ground so much that they couldn't use it anymore. And so there are some examples of that. I can think of a couple in North Dakota, a couple in the western states where yeah, we have seen that happen. And what that came down to was it was poor design. It was just we didn't balance the load properly, and yeah, we just just didn't take care of it well enough. But no, we do see that every once in a while if it's not designed properly. Yeah.
Okay.
Any other questions from the person? Okay, we have one last question from online.
Sure.
How does geothermal hold up with earthquakes, especially with countries like Japan and other rift zone countries, which have very frequent earthquakes?
That's a good question. Usually your surface stuff, your equipment isn't, how do I put this? I'm going to separate this into two sort of geothermal systems, right? I mean, you have your ambient temperature stuff where you're usually not going more than a few hundred feet deep. And very rarely does an earthquake damage those. Of course, you have really big earthquakes that cause liquefaction, and you're gonna ruin the system. And I think that's a part of living in those areas where there's just such widespread destruction. I don't know how to combat that exactly. But I mean, your larger high temperature systems have to deal with that a lot, and they design casings to be able to withstand that. You do have issues though where you have an earthquake and it can change the fractures underground, and then you get into really complicated stuff where, well, we had a well that was drilled in a fracture that was getting a lot of water, and now this earthquake has changed the fractures and we're not getting the same amount of water, and it's a different temperature and it's a different chemical composition. And I mean, stuff like that happens, and it's case by case, and it's a really complicated problem to solve. So it's a good question, and that's something that researchers are thinking about.
Okay, one more question, because I actually like this question.
Sure.
Can performance and energy savings be monitored? Do you know if a 6-pipe water-to-water heat pump system can be set up with geothermal at a later time? Is it just a matter of changing the heat source?
With a what pipe system?
Water-to-water, a 6-pipe water-to-water heat pump system.
I'm gonna be honest with you. This is a little above my pay grade. I'm a little more the subsurface guy. I'd love to get you in contact with our pipe guy. Sorry, I don't know much about that.
Do you want to go ahead and answer that?
Yeah, if I'm understanding the question correct, they're asking if they can go from a closed loop to an open loop. And if that's the question, then yeah, it's pretty simple to do.
Okay. All right, well, thank you very much, everyone. Appreciate you for joining us today, and thank you, Carter, for the lecture.
Yeah, thanks for having me.
Thank you, Carter.
Thank you.